Welcome to another video. Today we're going to demonstrate experiment number 14 in our lab manual. The experiment is titled Heat Effects and Calorimetry. The experiment consists of 4 parts, part A, B, C, and D. We are only going to demonstrate part A, B, and C in this video because these are the 3 parts that we will perform in the lab. Part A is titled Specific Heat. Part B is titled Heat of a Solution, and Part C is titled Heat of Neutralization. Part A is titled Specific Heat, and here we are going to look at the specific heat capacity of an unknown metal and try to determine what its specific heat capacity, and from there approximate its molar mass. Okay, so today we are going to look at thermal energy, which is sometimes referred to as heat energy. If 2 objects have different temperatures, are in contact with each other for a sufficient amount of time, both objects will eventually come to the same temperature. That temperature we call equilibrium temperature. The object that has a high temperature will transfer all of its energy to the object that has a lower temperature. So, what is the definition of specific heat capacity? Specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Water happens to have a very high specific heat capacity. The specific heat capacity of water is 4.184 joules per gram degree. Okay, that means in order for me to raise 1 gram of water by 1 degree Celsius, I need to input 4.184 joules of energy. Now, let's demonstrate how to do part A. In order to do part A, first I need to fill up a 400 ml beaker of water with deionized water and put it on a hot plate. I will set the hot plate here to about 7 setting, and we should do this first because water takes a very long time for it to reach boiling. I already preheated this water before we began the video. Okay, this way it does not take as long. Okay. Second, we need to get a calorimeter. Now we are going to use 2 styrofoam cups nested together with a cover, okay, as our calorimeter. This is a very cheap calorimeter. Of course, calorimeters could be very, very expensive. And the job of the calorimeter is to hold the heat of the temperature inside, okay, and not allow the temperature to escape into the atmosphere. So they have a very good insulator. And styrofoam cups are really good insulators. When we drink coffee or tea in them, we could have a very hot beverage inside the styrofoam cup, but while we're holding it in our hands, we don't feel that heat because the styrofoam acts as a good insulator and doesn't allow the heat to escape into the environment. Very different from holding a hot glass cup or a hot beaker that has boiling water in it. Of course, we'll burn our hand because glass is not a good insulator. Okay, so this here is going to act as our calorimeter. We should also get a thermometer. Now, I'm going to use a digital thermometer that has a metal probe. If you are using a glass thermometer, you should also obtain a glass rod. Okay, and if you're using a glass thermometer, you should make 2 holes inside your cover. One for the stirring rod, one for the glass thermometer. But since I am using a digital thermometer that has a metal probe, I'm only going to have 1 hole inside to check the temperature of the solution and of water and of the solution. So I'm going to use the metal as a stirrer. Okay. I will also get a 50 ml graduated cylinder, 100 ml beaker. Okay. I will get a test tube with a rubber stopper on it. If a rubber stopper is not available, that's okay. Okay. The first thing that I'm going to do is I'm going to obtain my unknown metal, and I need to know, this is a quantitative experiment, so I really need to measure the mass of my metal very well. Now, just like you guys have in your labs an analytical balance, I have an analytical balance right here, and I will weigh this metal to 4 decimal places. Okay, so what I will do, okay, is I will put a beaker inside because I really need to measure the mass of the test tube and the rubber stopper empty. And since the test tube cannot stand inside the balance, I will put a beaker, I will zero the balance, and now I will put my test tube inside, and I will record its empty mass. And the empty mass of this test tube is 26.0540 grams. Again, the mass is 26.0540 grams. Okay? I will put all of my metal inside the test tube. I'm going to use a weighing rope to help me do that so I don't lose any of the metal. It's very important. We're going to do 2 trials of this experiment. It's very important not to lose any of the metal. If we do lose the metal, we have to repeat all of the measurements. Okay? So here are all my metals going into my test tube. Okay. And now, again, I will make sure my balance is 0 with the test tube. I will put the test tube, the rubber stopper, and the metal inside. I will measure the mass, and the mass is 78.2703 grams. Again, 78.2703 grams. So between these 2 masses, I now know exactly how much unknown metal I have to start my reaction. So as you can see, my water already, because I preheated it, it starts to boil. But you really need to make sure you boil your water. You need to make sure that you incubate the metal in boiling water for 10 minutes. Now, my water hasn't fully boiled yet, but I could still put the metal inside before the water begins to boil. But it's very important that you begin your timer after the water boils. Okay? You do not begin the 10-minute timer before the water boils. The metal has to really sit in boiling water for 10 minutes. Water boils at 100 degrees Celsius. I want to begin with a metal that has an initial temperature of 100 degrees. So that means it has to be sitting in boiling water for a sufficient amount of time for all of that energy to transfer and the metal to have 100 degrees Celsius initial temperature. Also, I must make sure that my water inside my beaker covers the level of my metal. If my metal is sticking out in the air, the part that's sticking out in the air will not be at 100 degrees Celsius. Okay, so now I'm going to test, and I see that my metal is below the level of water, which is good. If I see that the metal is above, there's 2 things I can do. If there's still room in my beaker, I can add water. If there isn't enough space, what I need to do is take some metal out and re-weigh the metal that I begin with. But this here is good, so I'm going to keep that mass of the metal that I have. I will subtract the 2 masses together. This is called mass by difference, and I will obtain the mass of the metal. Okay, I'm going to let this reach boiling, and once the water begins to boil, I'll begin my timer and let it incubate in boiling water for 10 minutes. Meanwhile, I will get my calorimeter, okay, and I will weigh my calorimeter obtain the mass of the empty calorimeter. So I will make sure that my balance is 0. I will weigh both nested cups together with the cover. The mass of the empty calorimeter by itself is 8.7811 gram. Again, the mass is 8.7811 gram. Okay, so now I have the mass of the calorimeter. Next, I'm going to do 2 trials. The first trial requires 40 mLs of water. The second trial will require 50 mLs of water. Okay, now I will obtain 40 mLs of the ionized water, and I'm going to measure it in a graduated cylinder. If the volume goes a little bit above 40, it's okay. If it goes a little bit below 40, that's okay, because what's really important is the mass of water that I have in my calorimeter. That's why I pre-weighed my empty calorimeter, and I know the mass of it empty. And now I will add my approximately 40 mLs of water into my calorimeter. I'll put the cover back on it, and now I will measure the mass of the water and the calorimeter to know exactly how much water, how many grams of water my trial has. Okay, and now the mass of the calorimeter and water is 48.1396. Okay, again, 48.1396 grams is the mass of my water and my calorimeter. So now this is ready. Okay, I just need to wait 10 minutes for the metal to incubate in boiling water. So you see now the water started to boil. Okay, now I can begin my timer. Okay, and I will wait 10 minutes for this to boil. Okay, and when we come back after 10 minutes, we'll continue the experiment. Okay, so we're back. It's been 10 minutes. The metal's been sitting in boiling water for 10 minutes. So now the initial temperature of this unknown metal should be 100 degrees Celsius. And we're going to assume it's 100 degrees Celsius because it's been sitting in boiling water for 10 minutes. So all of the thermal energy that was in the water transferred to the metal. Since water boils at 100 degrees Celsius, okay, that same energy is now transferred to the metal, and the metal has 100 degrees Celsius initial temperature. Okay, we already have our measured 40 mLs of water. We measured it very accurately on the analytical balance. We also measured the metal on the analytical balance very accurately. Now what we will do is we'll get our thermometer, we'll turn it on, and we will measure the initial temperature of water inside the calorimeter. Okay, if you see the temperature fluctuate, wait until the temperature stabilizes. So right now, my temperature was at 25.1 degrees. It went up to 25.2 degrees. I will wait to see if it goes up to 25.3. If it doesn't, I will record 25.2 as my initial temperature of water. Okay? And it seems it's steady, so my initial temperature is 25.2 degrees. Okay? What I will do next is, okay, I will just, so I don't want my thermometer and cover to pick up any contamination from the bench, I will just get a piece of paper towel. Okay. And I'll get a second piece of paper towel. Okay, and this second piece of paper towel, I'm going to wipe off any hot liquid that's on the outside of the metal. I will do this very quickly, be careful. The test tube is very hot. I'm going to take off the rubber stopper. I will put all of the hot metal inside and quickly close the lid and I will mix and monitor the maximum temperature that my thermometer will read. Okay, just make sure you give it a good mix inside. This way all of the energy that the metal contained will be transferred to the water. Now I began at 25.2 degrees Celsius. My current water temperature is 32.7 and it just jumped up to 32.8. I will wait to see if it goes up to 32.9 or if it goes down to 32.7. I'm looking for the maximum temperature, and now it seems that it went down to 32.7, so I will record my maximum temperature, my equilibrium temperature at 32.8 degrees Celsius. Okay, so to recap, the initial temperature of the metal, because it was sitting in boiling water, it was 100 degrees Celsius. The initial temperature of water, of my 40 mLs of water, was 25.2, and the equilibrium temperature of both the metal and the water is 32.8 degrees. Now, the next step that I need to do is I want to make sure that I maintain the equal level of water inside my beaker, because you see water evaporates very quickly. I have to do a second trial. Okay, so I want to make sure that I fill my water bath. Okay, this way when I put the test tube inside, okay, I will make sure that all of the metal is covered with water. Okay, of course I have to wait again for the water to come to be brought to boiling, but that should not take as long as the first time. Okay, so always keep the water, always keep the heat on. Okay, this way you don't waste time. Okay, now I will take my thermometer out. I will put it back here for protection. Okay, and what I will do is I will get rid of the water that's in here. Okay, just make sure you don't lose any of the metal. If we lose any of the metal, we have to reweigh, okay, the metal and the test tube again. If we don't lose any of the metal, okay, we could keep the same mass of the test tube, because the test tube's mass, empty, will not change. If I don't lose any of the metal, the mass of the metal will also not change, and I could reuse that. Okay, so I'm going to be very careful. Okay, I'm going to pour out my water, okay, without losing any of my metal. Okay, and what I will do next is I want to make sure that all of my metal is dry. So I will bring a piece of paper towel. I will put all of my metal on it. Okay, I will dry the inside. Okay, this is now ready for the second trial. I will also dry the cover. Okay, wipe the outside. Okay, I will get another piece of paper towel. Okay, to make sure that I dry all of the metal. Be careful, don't lose any. Like I said, if we lose any of it, we have to reweigh it. I'm going to move the metal onto a dry spot on the towel. Okay. I will put the other piece of paper towel on it. Press to absorb any liquid that's on here. If we do a good job, okay, the metal will be nice and dry. Okay, I will put back all of the metal. Okay, you could use a beaker, or you could use, actually we could just bring this beaker here. I'll use a beaker instead of a weighing boat. Okay, I will put all of the metal into the beaker. Okay, the metal should now be dry. Okay, I will put the metal back in the test tube, And since I didn't lose any of the metal, I don't have to reweigh it. Okay, because the mass of the metal, the mass of the test tube, since I didn't lose any, will remain constant. And now I could wait until the water comes to a boiling, okay, and begin my timer. But meantime, I'm going to have my metal sitting in this water until it comes to a boil, okay? And now I could do the second trial, repeat everything over again for the second trial, but now instead of using 40 mLs of water, I will use 50 mLs of water, okay? Now the mass of the test tube, empty, should remain the same. The mass of the metal and the test tube should remain the same because I didn't lose any metal. Okay, so the initial mass that I measured in the first experiment, in the first trial, will remain the same. The mass of the empty calorimeter, okay, again, will remain constant, will not change. But the mass of the calorimeter and the water will be different because the first trial I used 40 mLs, but for the second trial I will use 50. So of course the mass with 50 mLs, okay, will be more than for 40 mLs. So you need to make sure that when you add your 50 mLs of water, okay, reweigh your calorimeter with 50 mLs of water. And I will put it onto my balance after zeroing it. And the mass now is 57.8626. Again, 57.8626 grams. Okay, and now I can wait, okay, until water comes to a boil. Incubate the metal in boiling water for 10 minutes and begin the second trial. Okay? Okay, now we're going to do part B of the experiment titled Heat of a Solution. I will reuse the calorimeter that I used in part A, and because I'm reusing the same calorimeter, the same 2 cups, the same lid, I don't have to take the mass of the calorimeter empty. Okay? But I will obtain an unknown solid, and this unknown solid here, okay, I'm going to measure its mass exact, and I'm going to dissolve it in a measured amount of water inside the calorimeter and monitor the temperature of water to see if dissolving the solid is an endothermic process or an exothermic process. If dissolving the solid in water is an endothermic process, means it requires energy, it will obtain the energy to dissolve it from the water molecules surrounding it, and I will notice that there will be a decrease in the temperature of water. If the dissolving is an exothermic process, the reverse will happen. It will give off energy as it's dissolving, and the energy will be absorbed by the water molecules, and this will increase the temperature of water. From doing this experiment of part A, I'll be able to determine the enthalpy of this solid. Okay, the enthalpy of the solid, if I obtain a positive enthalpy, that means it's an endothermic process. If I obtain a negative enthalpy, this will be an exothermic process. But we'll leave that explanation fit for the other video, the calculation video. Let's start the process and see how we'll do it. Okay? First, I already obtained in part A the mass of the calorimeter empty. I don't need to obtain it again unless something went wrong with my cups and I punctured a hole in it, or I'm using different cups and different lid for any reason. I'm reusing the same ones, so the mass of the empty calorimeter I will obtain from part A, and what I will do is now measure the mass of water by difference. I will get my 50 ml graduated cylinder and I will measure 50 mLs of water. Now I went a little bit over 50 mLs, but that's okay because I'm going to measure the exact mass of water that I have here, okay, by mass difference. So we already have the mass of the calorimeter empty from part A. Now I will zero my balance and measure the mass of the calorimeter and 50 mLs of water. And the mass that I'm getting is 60.1164. So that's 60.1164 grams. That's the water and the calorimeter. Next, I need to measure exactly how much solids I'm going to add to this water. So I'm going to get my unknown solid. I will get a 50 ml beaker. First, I will weigh the beaker empty. So after zeroing the balance, I will measure the mass of the beaker. The mass of the beaker is 29.9359. Again, 29.9359 grams. I will transfer my solid to the beaker. Now I will weigh the beaker and the solid. The beaker and the solid weigh 35.1321 grams. Again, it weighs 35.1321 grams for the beaker and the solid, and by taking the difference between the two measurements, I know exactly how much solid I have in my beaker. Next part, okay, I will measure the water temperature, the initial water temperature. So I'm going to take my thermometer, I'm going to insert it into the water and see what the temperature is for water. Now, water should be around room temperature, okay? And right now, I have a temperature of 25.1 degrees Celsius. So what I will do is I will take off the cover. Okay, make sure you don't it doesn't pick up any contamination from the bench. Okay, now I'm going to add the solid to the water, and I'm going to look to see if the temperature of water increases. That means it's an exothermic process. If the temperature of water decreases, it will be an endothermic process. Now, make sure you add all of the solid in your beaker inside the calorimeter, and also make sure that you mix it very well. All of the solid must dissolve in the water to get an accurate enthalpy calculation at the end. Okay, so I'm going to add my solid. I'm going to put my cover on with the thermometer. I'm going to start to mix. Okay, now I already know that this is an exothermic process because my temperature is increasing. Now I'm going to keep on monitoring the increase in the temperature until I reach the maximum. Right now we're at 33.7. I'm going to see if the temperature will climb. Okay, climb to 33.8. And I'm going to continue mixing and monitor the temperature. Now the temperature increased to 33.9 degrees. I will see if it reaches 34. Right now I'm at 33.9. Keep mixing, make sure all of the solid is dissolved. Now my temperature started to decrease. It went down to 33.8. I will continue to monitor it. So the highest temperature I reached is 33.9 degrees. Now it continues to go down to 33.7. So the highest temperature that I reach is 33.9 degrees. I began the water temperature at 25.1 degrees Celsius and it reached 33.9 degrees. And I'm going to check, make sure that all of my solid dissolves, and it seems that all of my solid did dissolve. Okay, and this solid, dissolving this solid in water is an exothermic process. Okay, now we can do our calculation and determine exactly what the entropy of this solid is. Okay, now we should get rid of the solution. The unknown solutions are non-hazardous, so they could actually be dumped down the drain. We should rinse the cup with some deionized water, clean it and dry it, and get it ready for part C of the experiment. So I'm going to go do that, okay, and I'll come back and I'll show you part C of the experiment. Okay, so now we are ready to do the last part of the experiment, which is the heat of neutralization. For heat of neutralization, we will go to the hood and obtain 25 mLs of sodium hydroxide as well as 25 mLs of hydrochloric acid, neutralize them together, and calculate the entropy of neutralization. Now, neutralizations are exothermic reactions. Whenever an acid neutralizes a base or vice versa, energy is given off, and you could feel that in a reaction tube or in a beaker where the reaction is taking place, and you always feel that the reaction is getting warm. Okay, so here we expect to see an exothermic reaction, so we expect the temperature of the solutions to increase. So if we follow the procedure, I've already done, I rinsed the calorimeter with some deionized water, and I also dried it, so my calorimeter is ready. I already went to the hood and I obtained in a beaker a few mLs of sodium hydroxide and a few mLs of HCl, hydrochloric acid. If we follow the procedure begins with hydrochloric acid. It says measure 25 mLs of hydrochloric acid. Here I'm going to be very careful, so I'm also going to use the disposable droppers to make sure that I get exactly 25 mLs, and I will pour 25 mLs. Okay. And to get to the meniscus exactly, I'll use a dropper, and so now I have 25 mLs of hydrochloric acid. I will pour the 25 mLs of hydrochloric acid in my calorimeter. I'll cover it. I will get some deionized water, and I will rinse my graduated cylinder with deionized water. This way I get rid of all the traces of hydrochloric acid. I will do a second rinse just to be sure. I will flip this upside down just to try to dry it as best as possible, because I don't want to dilute my base once I start to add it. Now this is ready to measure 25 mLs of sodium hydroxide. So again, I'll measure 25 mLs of sodium hydroxide very carefully. I'll get another disposable pipette, and I'll bring the volume to the meniscus. And now I have sodium hydroxide in my graduated cylinder. I have hydrochloric acid in my calorimeter. I'm going to get the initial temperature of both solutions. If the initial temperature of both solutions are different, then I'm going to use their average, and I'll show you how to do that in the calculation video. I will use their average as the initial temperature. If their temperatures are exactly the same, and most likely their temperature will be exactly the same because they've been sitting at room temperature for quite some time, but sometimes they're off by 0.1 or 0.2 degree. So I'm going to take my thermometer. First I'm going to measure the temperature of the acid, and I'm going to record it. Okay. So the temperature is decreasing. I'm waiting for it to stabilize. And now the temperature of my acid is 24.6 degrees. It just went down to 24.5. So let me just swirl it and see if it stabilizes at 24.5. So now it's stable at 24.4 degrees. So my temperature of the acid is 24.4 degrees. I will wipe the thermometer. This way I don't have any neutralization taking place. Okay? And now I will insert the thermometer in my base to see what the temperature of the base is. And now my base stabilized at 24.6 degrees. So my acid is 24.4, my base is 24.6. I'm going to take the average of the two, and I'm going to say my initial temperature is 24.5 degrees. Okay. So now I could wipe the thermometer. Okay, I will rinse it with some deionized water and put it back later. Okay. Okay, so now we are ready to mix the two solutions together. Okay. I will get my thermometer ready. Okay. And what I will do, so now I'm starting at an initial temperature of 24.5 degrees. I expect the temperature to increase, so I'm going to mix the two together, put the thermometer in there, and monitor the highest temperature, the maximum temperature I approach, that I reach. And now I will mix. My temperature is increasing, neutralization is occurring. I am currently at 36.4 and climbing. 37.2. 37.3. Continue mixing. I reach 37.4. Continue mixing. I just went down to 37.3, so it seems that the temperature is starting to descend, starting to go down. Now it's down to 37.2. I can stop, and the highest temperature I reached is 37.4 degrees Celsius. So I started at 24.5 degrees Celsius, and I reached 37.4 degrees Celsius. And that's the end of the experiment. I'll see you guys in another video where we're going to learn the calculations for this experiment.